Let's get started then. Uh, Hi again, folks. Hope you're all having a great day. Welcome to YFTT talks for tech talks for engineers by our engineers. I'm Sandeep Lingam. I'm one of the directors here at Yogabyte on the core database team. And my team works on features like Xcluster, Backup Restore, PITR, and now Clone. Today we have two engineers from my team, Anubhav Srivastav and Yamin Haddad, who are going to present a super interesting feature that we've been working on for the past few months called instant database cloning. Uh, Anubhav, Yamin, take it away.
Cool. Yeah, thanks, Sandeep. So yeah, like Sandeep said, we're going to be talking about instant database cloning, which is something that Yaman and I have been working on for a few months now. So again, thank you for joining us. So we're going to start with some motivation, what clone is and why you want to use it. Then we'll talk about how you actually use it, the kind of extensions to PG syntax that we've introduced. Then it's Yaman's portion where he's going to talk about, he's going to show you a demo of some of the scenarios we talked about, and then he'll take an inside look under the hood of how clone actually works. And we'll have some time for Q&A after, but also feel free to drop your questions in the chat, either on YouTube or on LinkedIn, and we'll pick them up and handle them as the talk goes on. Okay, so let's start with a scenario that's all too common. You have two tables in a production database. You have a business metrics table and you have a customer data table. And one day you accidentally drop your metrics table, let's say at 9 o'clock. And of course, you want to recover your metrics table. So how do you do that? In Yugabyte right now, our solution is point-in-time recovery. So the way point-in-time recovery works is you set up what's called a snapshot schedule, and that gives you a data retention window of a configurable amount of time. So if it's 24 hours, what that means is any deletes that happen in the last 24 hours don't actually take place until that 24-hour mark, which means you can continuously restore your database in place to any time in the last 24 hours. So in the case of where you drop the metrics table at 9 a.m., you would do a PITR to just before 9 a.m., and that would roll back your database to just before then. And PITR is great for cases where you have corruption on your entire database and you really just need to go back to a point of time in your retention window. But what if you only want to restore one table? So you only want to restore the metrics table. And for that, clone is a much better alternative. The way clone works is it creates a copy of the production database as of a point in time. So in this case, we're creating a clone of the prod database as of just before 9 o'clock. And there are two features that make clone super exciting. The first is that it's fast, so there's no data copying required to clone the database. And the second is that it's independent, which means that the reads and writes on the clone database, they happen completely independent of the production database. So you can read and write to your clone and it won't affect your production database at all. And because it's fast, that means you can copy some multi-terabyte clusters in a matter of seconds, as Yaman will show in his demo.
Do we just clone a single table, or do we need to clone the whole database?
Yeah, so that's a good question. We do need to clone the entire database, and similarly for point-in-time recovery, we have to recover the entire database. And the reason for that is essentially some consistency guarantees within a database. So if I have a transaction, it can affect two tables in a database in a way like, for example, a user may say that every row they insert gets inserted into metrics and into the business data table. But if we roll back just the metrics or just the customer data table, what happens is we've broken the user's their own guarantee about a row being in both databases at once. So while we can't generically roll back the entire just one table of the database, we have to roll back the whole database. Once you've done the clone, you can selectively copy the metrics table from the clone database back into prod. And then it's up to the user to guarantee that they're not violating any of their own invariants.
I guess it's important to do this to preserve sort of cross-table transactional consistency and
Yeah,
whatnot.
yeah.
Got it. Okay.
Okay. So that's the scenario where you accidentally dropped a table. Another scenario where you might find clone is useful is if you want to do some upgrade testing on your app. So let's say we have the same example as before. You have a production database with your customer data table, and you want to add a user age column. So the command for this is alter table, and you add column user age. And there's kind of two ways to do this without clone. The first is you can test in a smaller environment with less data, but then you might miss an edge case that's only in your real data and not in your test. Or you can copy all your data out, but if this is and then re-import into a different universe. But if it's a multi-terabyte database, it's going to take maybe hours to copy that data out. And why do you want to do that when you could just use clone? So instead with clone, you're going to create an instant clone of the database, of your production database, and you can run your alter on your clone and point your app towards your new towards your clone database. And what that'll let you do is it'll let you test the new schema without having to either copy all the data out, and you can test on actual production data. So,
and I guess if you proceed to upgrade your production data, and if you encounter an issue, you can quickly, I guess, fall back to your clone also.
Yes. Yeah. Or you could even clone as a point in time, again, from your production database. Okay, so that's kind of the two scenarios we wanted to talk about. And let's look at how you actually implement this in YSQL. So there's some existing Postgres syntax for cloning, kind of. It's called template. And for example, doing create database foo template bar, we'll create a database called foo and copy all the data from bar. By default, if you don't give it template bar, create database foo copies from a Postgres template table called template1, which some of you may know. And the Yugabyte syntax is almost the same. We just have this additional as of timestamp, where timestamp is it's just a Unix timestamp. And if you leave this off, it's identical to the Postgres syntax. You just create a clone as of now. So the Yugabyte syntax has the same permission requirements as Postgres. You still need to be able to create database. You still need to be able to read from the template database. And it also requires a snapshot schedule, just like PITR did in the first example, where it retains history for 24 hours. So if you want to clone to 9 o'clock, you have to still have the data from 9 o'clock. So you do need a snapshot schedule to retain that history. Okay, so I'll turn it over to Yamin for the demo right now.
Yeah, sure. Let me share my screen. Do you manage to see my screen now?
Not quite yet.
Not yet.
What about now?
Not yet.
Oh, there it is.
Yeah.
I think now it's working. Okay. So yeah, thanks Anubhav. Let me go right into the demo. But first of all, let me give an overview what we are going to demo today. So I will use the TPCC benchmark. It's a known database that is used for testing OLTP databases. Now, usually it's represented in terms of the number of warehouses. So now we will use the 12,000 warehouses. That's approximately 770 gigabytes of data. And because we replicate the data 3 times in Yugabytes, so we have the total size of data is about 2.3 terabyte of data. Now, what we will do is we will simulate a drop table by mistake, and then we will clone to a time before this drop happened. Secondly, we will create a development database as a clone of the production one, and then we will perform some DDL changes, test if it works or not. And thirdly, we will insert rows to both the development and the production database so that we can show the isolation, like whatever we write on the first database doesn't affect the writes on the other one. And without further ado, let me jump directly to the demo. So here I have 2 terminals. The one on the right, I will use it for the production database, and the one on the left for the clone. So now I will connect to my cluster using the YSQL SH.
I think just quick clarification, the other way, the one on the left is the production one, the one on the right is clone.
Yeah, okay, depending on the screen, yes. But so this is prod. I mean, I call them production database, and the other one will be clone, so
yep.
things will be clear.
Should be
yeah,
pretty
so this is the production database. Now, if I try to describe the tables, so this is the TPCC schema. So basically, it's an inventory management schema. We have customers, we have stock, warehouses, we have orders. Now, I have this query which shows me the size of every table in the database. So here I'm just showing every table and its size. We can see, for example, the customer size is 200 gigabytes, the stock is 350, the order line 150 gigabytes. So the total size is like around 750 gigabytes. And as we said, we usually express the size of the TPCC benchmark by the number of the warehouses. So here, if I do select count start from warehouses, we have 12,000. Now let's simulate a drop table. But before that, Because now the database in the correct state, let's just take the timestamp, the correct timestamp. We have this simple Postgres query that gives us the timestamp in Linux, milliseconds. The main idea here is that this is the point we want to go back to. Now, let's simulate the table drop. Here we are dropping the table warehouse, and it's dropped. Now let's try to query this table. If we try to query it, it will not work. Why? Because simply the relation warehouse does not exist. Oops, what can we do? Well, luckily we can perform clone, and clone is as easy as this SQL instruction that Anubhav shared with us. What we are telling here is we want to create a new database that we call it clone DB, using as a template the production database as of the point in time that we just copied here before the drop table, where the state of the database was increasing. This is 590, this is 590. And now the clone is taking place.
And Yaman, I guess if we are unsure of what the timestamp is, if you have some kind of auditing enabled, you could kind of look through the history to figure out what time a certain operation may have happened.
Yeah, right? Definitely. If you have DDL log enable or DDL auditing.
Yeah.
Yes, perfect. And you can even do trial and error, right? Like there's nothing wrong if you clone, like you can do binary search, or like, I'm kind of complicating it, but yeah, you can clone as much times as you want, so you can test it yourself. So now we are connecting to the clone database here on the other terminal. And if I do listing for the tables, we can see that we have the warehouse. So luckily we are able to get it back. While if I check in the production database, we don't have the warehouse. And I can just run a select star from the warehouse. We have all the 12,000 rows. That's the first example.
And I guess one more question, as noticing as you were doing the drop, it also cascaded and dropped the constraint. Would the constraint also get?
Exactly. Yes, definitely. So here, if I do, like, for example, for the warehouse, unfortunately, here we don't have it because we just dropped it. But yeah, here I can just show the schema of the warehouse. So here we took the indexes, the primary key one, and the two constraints, the two foreign keys that we dropped right before the drop of two other objects, the two constraints. So yeah, we copy all the schema and all the data. You have the state of the database exactly as it was, like at the clone time. Now, for the second part, we want to simulate basically, creating a development database. And let's say we want to do a migration. And here the migration that I would like to do is, let's say we want to add a column. Oh, by the way, I forgot to show you, for example, here, we can check the size of the clone. We can see that we cloned all of them. This is 200 gigabytes. This is 350. This is 150. So this is 2 terabytes. There is no way we can copy 2 terabytes within like a few seconds. Yeah,
so
going back
you're not worried about running out of disk here, Yaman, on the clone database?
Yeah, exactly, not at all. So here we didn't copy any extra space. I mean, we are just using hard links. Mm-hmm. So we don't have 4 terabytes of data. We have 2.3, the exact same number. Mm-hmm. Yeah, so here now we started by creating the development database. Now I can just, here, for example, I can list databases. I have the clone, I have the dev. Let's connect to the DivDB. Okay, now I can check. What do we have here? We have all the tables, except, for example, of the warehouse, because we dropped it. Now, let's say the DDL that I want to perform is on the table called item. So what does the item table contains? It has the ID, it has the name of the item, it has the price, some data, and image ID. Let's say now we want to upgrade the database. We want to add a category. And that is performed, we can just test it by doing alter table item. We are adding the column category of type text. Now we performed it on the dev. We are trying, we are testing. There is nothing wrong here. We see we managed to insert this column, while here in the production database, we still have the old schema. We can see here we don't have the category. Now, I want to show that we can even, let's say now the next step is we want to test inserting DMLs according to the new schema. So here I did a select on the ID, name, price, and category. So here this is a new column from item. I'm doing just order by ID so that I have consistent result, and limit by 10 because we don't want to see like millions of rows. Now, the name here is randomized data because this is TPCC data, but like you can think about it as any items. Now, let's say the application is inserting rows according to the new schema. Here, what I did is insert into the table item. the values, like I started by ID 0. The item is, like, say, iPhone 13, the price, and here the category. It's a mobile phone. We can see that insert now passed successfully. I can run the same select query that I used to do. We can see here that the new row has been inserted according to the new schema. Now we have category. So things looks fine in dev. Now I can run the same query that I just ran before, the select star, on the production database, and we can see that it will fail. Why? Because simply the column category doesn't exist. And here when I'm doing a select, I'm doing select on the category. So I shouldn't run this query. What I should do is I should basically select according to the old schema. And at the same time here, we can show that the rows that we inserted on the clone doesn't interfere with the database, with the production database. The production database has like the old data. Now, let's say the production database is also receiving reads and writes. We want to see how it's isolated from the dev database. So here, if we insert into the same table values and also 0. So here, like if there is somehow interaction, we should have a primary key violation constraint, a new mobile phone, and it doesn't have that, like the new category. I can just run the select. We can see the new phone here. Now I can run the same select here, and we can see that there is no interference, like the data is different. Here we're inserting Samsung in production, and we're inserting like the iPhone in development database. So we have two independent databases. They accept reads and writes independently.
There is a question on the chat.
Yes.
Can we clone a petabyte of data without any issues?
Yes, in theory you should. Like there is nothing that can stop you. We are using hard links. So if you have your own, like the first database in the production, there it's a petabyte size. Yeah, you can just clone it without incurring any extra overhead.
I guess you'll be getting into the how in some of the subsequent slides.
Exactly. That's actually a good introduction into the showing you why we can do that. And to show you how we can do that, we want to go a little bit deeper on how clone works under the hood. And we want to answer mainly 3 questions. First one is, yeah, how do we manage to do clone? Like, how can we clone a petabyte of data somehow for free? The answer is like there is no extra data copying. The second question is, how do we manage to clone to a point in time in the past? And thirdly, how do we manage to isolate writes to database, like the clone database and the original database, so they can be completely in isolation? And to take an example, like here I have a Yugabyte cluster, which consists of 3 nodes and 2 tablets. Now the tablet is a partition of a table. So whenever we create a table in Yugabyte, we partition it into tablets so that we can distribute the workload. And each tablet basically is replicated for fault tolerance. So here we replicate tablet T1 into 3 copies, the same for T2, so that if one node failed, the 2 other nodes can take reads and writes, and the application doesn't feel anything. Now, let's focus for this demo on 1 tablet and 1 node, but whatever I will say for 1 tablet applies for all the tablets. So this is 1 tablet, T1. Now, how do we store the data under the hood? Well, Yugabyte use LSM storage architecture, and LSM stands for log structured merge. And in this type of storage, we don't update rows in place, meaning it's not the classical way where you have the table, you can imagine it in your head. If you want to update a row, you go to the place where this row existed and then remove the old data and update the new one. It's an append only data storage, meaning when we add new data, first of all, we add them in memory, and then we flush them every once in a while. So we start by flushing SST1. This file is like, it stands for sorted sequence table. Once it's flushed, it's immutable, meaning it will never change. And it has all the changes of the database between, let's say, 2 specific, like between 4 and 530. Now, let's say we want to update a row that exists in SST1. We don't go to SST1 and try to modify it there. Instead, we append the new row and we flush it into SST2, where we mention the new update. Again, SST2 is immutable. And if we want to update the same row, we don't update it in place. Instead, we append the new change in SST3. So we have like a set of files that are immutables, and they contain all the history and all the versions of the rows within a certain retention period. So here we have all the updates between 4 and 645. Now that we lay the background, I think it's kind of easy to understand now how do we manage to do clone. So if we create a tablet T1 prime as a clone of tablet T1, what we do under the hood is we create a logical tablet T1 prime, but as a data directory or as like data files, we use the same data files of T1. And we do that using hard links. So we are pointing to the same set of SSD files. That's why we don't incur any extra copying. And okay,
to schema though? What happens to schema though?
Yeah, so this is on the data layer. Now on the metadata layer, what we do is we are creating the schema as of point in time using like YSQL dump, and then we restore it there. So we regenerate the schema as it was in the past and recreate it as it was in the past. And then we link the old schema to the old data, to the set of data files. So schema is generated independently, but for data, which like in terms of size, this is what matters, like the data, we are using the same hard links and the same SSD files. For metadata, we generate the schema as of point in time.
I guess the assumption we're making is like it's okay to copy the schema effectively because schema size is negligible compared to the data sizes.
Exactly, definitely. I mean, like the size of like it's a few megabytes maybe. So it's not a big deal. Like it's a metadata at the end. Yeah, that's the analogy. But here we save on the betabyte or terabyte. We don't need to copy any of that. Now, and we make sure because SSD files are mutables, we make sure that when any writes come to T1, we will not affect the reads of T1 prime. Now, for the second part is like, okay, so how do we clone as of a point in time? Well, now that we talked about how LSM storage works, and because we store all the versions of the row within a certain period, retention period, now cloning as of time consists of simply adding a time filter. So here, for example, if we are creating a tablet T1 prime as clone of T1 as of 6, we just need to add a hybrid time filter. And what this time filter is telling us, whenever you want to read from T1 prime, just ignore all the newer versions that exist between 6 and 645. So we can read all the older updates as of 6. And this is how we get the as of time, basically, capability.
So does that time apply to both T1 and T1 prime?
Oh, no. That's a good question. Basically, T1 prime, the time filter is per tablet. So here, T1, if we want to perform reads on T1 is not affected. It can read all the data as of like 645, like as of most recent data. So we have one time filter per tablet.
Got it.
So this, it's only avoiding T1 prime, like reading newer updates, yeah. Now the third question, and this is actually explained here, like if we zoom in a little bit more into this. Now here I want to show like, how do we manage to isolate reads and writes for the two databases? Here, if we can see a little bit different perspective. Now here we have tablet T1 and tablet T1 prime. Each one has his own data directory. And to take in the same example, if we do create T1 prime as clone of T1 as of 6, what is happening is we are creating a new data directory for T1 prime. Now, because we are cloning as of 6, we only need the data of SST1 and SST2. And that's what we put here. And they are in dashed because they are hard links. So those are not actual files. They are just pointers to the original files, let's say. Now, if we are doing or performing writes to the tablet T1, they will go to their own space in memory, and they will be flushed to their own set of SSD files. So here, all the new writes to T1 goes to SST4, and T1 prime doesn't know about that. And the same for T1 prime, all the writes that goes to T1 prime, they are going to their own memory, and then they are flushed to their own set of SSD files. Here, for example, it's SST3 prime and SST4 prime. And here we can see that writes to one database doesn't affect the writes to the other.
And the time filter, earlier you had said that it's per tablet. So will that time filter not apply to the newer files, or how does that work?
Oh, yes. So the time filter only applies to older files. Like those new files, we read them because they are considered new, right? They have new data. So yeah, we read SST3 prime and SST4 prime. So the hybrid time filter is per tablet, per older file, let's say. Yeah. Now, also I want to talk about how compaction works. So let's say, because we are at LSM storage, we always have compaction going around. So let's say here we perform the compaction on the tablet T1, which means we will remove the SST files 2, 3, and 4 and replace them with SST5. Now, what will happen under the hood is nothing will be affected for T1 prime. We will not delete SST2. Why? Because it's kind of like a shared pointer, or we have reference counting. We have 2 pointers on SST2. Now, after the compaction, we only have 1 pointer, but we keep SST2. But now it became only attributed to T1 prime. So here we can consider it somehow, maybe it's a space simplification, because now SST2 only exists because T1 prime is there. So this is kind of attributed to the clone only. But we don't delete any data. Like, it's not like T1 prime will disappear somehow because there is a compaction on T1. No, they are two independent tablets.
So is it fair to say that when clone is created, there is no copy involved, but subsequently, if compactions happen, then depending on what files are impacted by compaction, you're consuming a little more space than just 0.
Exactly. Yes. Yes.
Got it.
Yeah, and the added space comes from SST5, not SST2. So here, SST5 is the new file, so that's going to be the amount of new space we use.
Got it.
I mean, somehow it depends. Like here, because T1 prime is the clone, so I would say the cost of clone here is SST2, not SST5.
Fair enough.
If you want to say like the extra space is SST2, yeah. But yeah, it's when we have compactions, the more compactions we have, the more the two databases started to diverge and have their own independent SSD files, if you want to say. Yeah, but initially there is 0 copying.
Great.
Yeah, thank you very much. Yeah. Any questions?
Do you guys want to talk about like what the current state of the feature is? Can people start trying it out?
Yeah, sure. So the feature is currently in tech preview, and there are some docs on the Yugabyte website. If you search for instant database cloning, they should help you get started. There's a couple of flags, G flags you need to set because it's in tech preview to allow you to use the feature. But once you set those, you should be good to go. If you have any bugs, please come find us. Please report them. And if we haven't already seen them, we'll be happy to take them up.
Yeah.
Yeah, that was great. Definitely helped everyone hopefully get a good understanding of kind of the insides of clone. I was curious about like one other scenario which is potentially possible. I'm guessing like if you have a multi-tenant use case and you have a template database that you want to create multiple copies of, I guess with vanilla Postgres, you would be physically making those copies. But with clone, you could quickly create clones and open those up for each of the tenants, is it?
Yes, definitely, yeah. And it's a 0 copy thing, right? It's a lightweight copy. And they start diverging once you start inserting new data.